second partials test. Right, so I'll give you the second partials test on that, on Monday's test. We'll start early at 10:30. But I will give you that one formula. But you need your other formulas. You need to know the Duff, the gradient, the total differential. You need to kind of know those guys. But this second partials test that we learned in 13.8, I'll just give it to you. You need that number 1 on your take-home quiz as a classic. Find the critical numbers and then do the second partials test to see if they're mins or maxes or saddle points. That's a pretty good one, by the way, number 1 on your take-home quiz. Here's one. I'm going to grab this one if you don't mind. So this is what I would call a word problem from 13.9, but it comes off of my, and there's some actually number 1, 2, 3, and 4. In 13.9 there's some like this. But then this comes off of my practice piece of paper, number 5. And what it says is, on my practice piece of paper, number 5, says, find the points on the surface that are closest to the origin. So find points on the surface, z squared equals xy plus 1. Find points on that surface that are closest to the origin. So this is kind of a good, to me this is an applied max-min problem from 13.9, so to speak. But now let's just check out the wording here. I'm supposed to find some point on this surface. You know what I'm going to call that point on that surface? I'm going to call it x, y, z. So I'm supposed to find some point on that surface that's closest to the origin. The origin, of course, is 0, 0, 0. And just what I want to do is take this word closest and interpret it a little differently. I mean, this is easy for smart people like you, but closest, I want to interpret that as closest. I want to say minimum distance. And once I use that phrase, then this problem falls into place, I think. I mean, what I need, I think, is to minimize the distance. And so I think I need to set up, this is a word problem, and you're not trying to find the maxes and mins on that surface. No, no, no. But you are trying to find the points that are closest to the origin. So that's minimum distance. I think I should set up a distance formula and then attempt to minimize it. And that means take its derivative, set it equal to 0, blah, 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 right? Well, what's a distance formula? It's the square root of the x minus the x squared, which, by the way, now that's x minus 0, so that's just x squared, y minus 0 squared, and z minus 0 squared. Yeah, so it's a 3D distance formula between 2 points, and we want to find the minimum distance. Now, to minimize things up here in our 3D world here, what we need is, what we learned in 13.8 was that I need the partial derivative with respect to x, and I should set it equal to 0, and I need the partial derivative with respect to y, and I should set it equal to 0. So I need those. But I got a problem. I got too many variables in here. I mean, when I minimize something, it's a function of x's and y's, and then I do this to try to minimize it or maximize it. But it needs to be a function of 2 variables, and what I've got is a function of 3 variables, and I don't like that. And this is typical of the word problems. There usually must be some other condition that helps me get rid of one of these variables.
You solve the original equation for z?
Well, or it's already solved for z squared. But yeah, the condition is that this point lives on this surface. And so therefore, that's the condition that is sort of a second equation. And I can use that. You said solve for z and plug it in here. Well, you're right. It's already solved for z squared, though. So I'll just plug that in here. and I get this. My z squared is xy plus 1. If you live on this surface, your z squared is this. And so that was the condition, is my point did live on this surface. So cool, I was able to substitute that, and now I have a function of 2 variables. Okay, I got another idea here. I don't like, I don't really necessarily want to take this derivative with this big square root on it. So here's this other funny idea from calculus, or from when you're trying to minimize a distance, maybe you set up a distance formula, which has a damn square root on it. All right. Turns out, hang on now, I've said this before in a lot of my classes. Let's see. You know, if you have these distances, this distance, this distance, this distance, this distance, this distance, one of them's a minimum. Okay, if you square them all, the minimum will still be the minimum. So what you can do, instead of dealing with this square root, is you can, instead of minimizing d, you can minimize the square of d. Now I don't really want to like call it d squared and I don't want to bring the 2 down. That's not what I want to do. So I just want to, what I want to say is, I got this new thing called the distance squared. and it's this expression without the square root. And this is what I want to minimize. It just helps, it just simplifies the math a little bit. Because I can ignore the square root is what I'm saying. I can minimize this new thing called distance squared.
Yeah, because it's not asking for that exact distance, it's the smallest.
It's not. It's asking for the points that have the smallest distance from the origin. So, I mean, if at some point they wanted to know the distance, then I better remember that the distance has the square root on it, and this thing ain't really the distance. This is the distance squared. So it's just dangerous to call this d, you know, because it ain't the distance. But you can work with this instead. So here we go. dx. I mean, I am calling it d, and I'm calling this d, and I'm taking the derivative with respect to x. What is it?
2x plus 1.
Good job. Yes. I'm going to take the derivative with respect to y. 2y plus x, right? That's interesting. I'm going to set these both equal to 0 and try to solve this system of equations. Is that what I'm doing? That is what I'm doing. This is kind of strange. Here I go. This y is actually equal to negative 2x. That's what y is. If I substitute it in for this y, that's negative 4x plus x, but it equals 0. This is leading me to x equals 0. And if I plug that in right there, that means y equals 0. Well, this is kind of strange. I mean, the closest point to 0, 0 is 0, 0. Wait a minute now. Wait a minute now. Wait a minute now. This is my x and y value. What is the z value? Well, how do I get z? If I have an x and a y, where is z? Where is z? Where is z? Oh, there it is. On the surface, if you're on the surface, and if you're at the point 0, 0 on this surface, guess what z is? Z squared is 1. Guess what z is? 1, or actually plus and minus 1 maybe. So you know what? I think I've answered the question. Again, I found a critical point. I didn't prove to you that it makes my distance a minimum, but it's the only damn critical point I got. So I'm pretty sure it's the answer. My critical point is the kind of the ordered pair 0, 0, but to answer the question, find the point on that surface that's closest to the origin. I think the answer is 0, 0, 1 or 0, 0, negative 1. And that question turned out to be a lot easier. I mean, in the end, it kind of fell on itself and turned out to be pretty easy. In the beginning, though, this was a decent problem to practice setting up. I didn't do one like this before. distance, a minimum distance problem. I don't know. I thought it was okay. There might be, that was number 5 on the practice. I'm trying to look for maybe some 13.9 min and max problems. Min and max problems. On your take-home quiz, you got one down there called number 9 on your take-home quiz. That's a pretty good one. Maybe we should talk about that. Let's talk about that. Another, so I'm up here kind of in 13.9 trying to do applied max-min problems here in 3D. Check out this number 9 on your take-home quiz. Number 9 on your take-home quiz says, find the volume of the largest rectangular box in the first octant with 3 faces in the coordinate planes and 1 vertex in this plane. Wow, that's kind of a complicated sentence. But what did they say? They said that I'm in 3D and I'm in the first octant, and I got an x-axis, a y-axis, and a z-axis. And what they said is I'm trying to come up with a box that lives in here. And what they said about this box is that 3 of its faces are in these coordinate planes. Oops. 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 3 of the faces are in the coordinate planes. Well, that's this. That's that wall in the XZ plane, that wall in the YZ plane, and this wall, this floor, in the XY plane. And then here's what they said. Then the other point, the vertex, they called it one of the vertices, one of the corners of the box, lives in this plane. Now, when I see a plane, I remember what it looks like, kind of. Maybe you do, maybe you don't. When we graphed these planes, what we used to do, they would come slicing through the first octant. You know, they would hit, let's see, we would plot points. We would plug in a 0 for x and a 0 for y, and we'd solve for z, and we'd get 4. And that means it hits the z-axis at 4. We plug in a 0 for x and a 0 for z, divide by 2, it hits the y-axis at 6. We plug in a 0 for y and a 0 for z, it hits the x-axis at 3. So there's a plane here, and this corner of the box lives in the plane. Touches that plane. I don't know how great, that's probably a bad picture. But that corner of the box out here is in this plane, or touching this plane, or lives in this plane. That's what that sentence said. Let me read it again. What the hell did it say? Find the volume of the largest box in the first octant with 3 faces in the coordinate planes and 1 vertex in this plane. So that's the concept. And we need to maximize the volume of the box. Okay, great. Can you come up with a volume equation? You got to maximize the volume of the box. What's the volume of the box? Well, that box comes out a certain distance called x, I think. I think it goes over a certain distance called y, and I think it goes up a certain distance called z. So I think the volume of the box is x times y times z. And if that's the equation I want to maximize, that means I want to do my derivative. I want to do Vx, set it equal to 0. I want to do Vy, set it equal to 0. But again, I pause for a moment and say, damn, there's too many variables. I want this to be a variable of x's and y's, a function of x's and y's. I don't want that damn z right there. So is there some condition that has to be met that might help me get rid of that z? Yeah, the condition that has to be met is this particular point, which, by the way, this particular point is out x over y and up z. This particular point, x comma y comma z, lives in this plane. So z equals 3z equals 12 minus 4x minus 2y, or z equals, divided by 3, 4/3 x minus 2/3 y. Yeah, that's the condition that has to be met. He lives in this plane. So I can use that equation for z, substitute in for this z, and get this volume formula. xy times this z. That's pretty cool. I mean, I don't know. I'm trying to explain this. I hope you're getting it. It makes sense. It's kind of, again, there's this typical strategy of these problems. You come up with a formula you want to do the derivative of. God dang it, there's too many variables. There must be a condition, a criteria that might, that has another equation that helps you get rid of one of those variables. And now it's a matter of maximizing or minimizing this dude. If I was you, I would distribute the xy and make it look a little nicer. 4xy minus 4/3 x squared y minus 2/3 xy squared. And now I would try to do these derivatives. What is the derivative with respect to x? With respect to x, it's a 4y minus 8/3 xy with respect to x minus 2/3 xy squared. No, I screwed that up. I'm taking the derivative with respect to x minus 2/3 y squared. Right. Let's do vy. Vy would be the derivative with respect to y. With respect to y, the derivative would be 4x minus 4/3 x squared minus with respect to y, minus 4/3 xy. Right. Derivative with respect to y. Yeah. Okay, now what? Well, I'm looking for critical numbers. So now I set this guy equal to 0, and I set this guy equal to 0. Listen, I'm going to show you a slick move right here. You're setting these equal to 0. That's a hell of two equations, two unknowns to try to solve for. But let me show you this. Factor it. If you factor out a y, you are left with 4 minus 8/3 x minus 2/3 y. On this one, I think you can factor out an x, leaving you 4 minus 4/3 x minus 4/3 y. If you're setting this equal to 0 now, you could set this equal to 0. You get y equals 0. You know, if y equals 0, your box ain't got no volume. You hear me? If y equals 0, your box ain't got no volume. So perhaps that's a critical number. It's a legitimate critical number that leads to a minimum volume because you ain't got no volume. You got a volume. So it's a critical number, but it's going to get, I'm going to ignore it. You know, I could also set this x equal to 0. I could work on trying, but if you're a box that has an x coordinate of 0, you got no volume. So these are not the critical numbers I'm interested in. These are kind of leading me nowhere. So then what I'm really more interested in then is, because when you have something factored, you set each factor equal to 0. So I tried to set this factor equal to 0 and talked you into that it doesn't matter, or it's not what I want. So I'm setting the other factor equal to 0. Okay, so I'm setting this equal to 0. And I'd set the x equal to 0 and talked you into saying that doesn't matter. So it's really about this other dude equaling 0. So now here I am. This is the two equations, two unknowns I'm trying to solve right here. And this will yield the critical number I want, I think. This will probably, solving this system of equations now will yield the critical number that maximizes my volume. Yeah, what's our best choice here? Solve and substitute or something. Let's see. Yeah, I'll just try to solve and substitute for y. If I add the 2/3 y over here, it'll be here. It'll equal this. Then I'll multiply by 3/2. So y will equal 3/2 times this will be 6. 3/2 times this will be this. Okay, there's y. Awesome. I think I'll go plug that in right here for this y and proceed to solve this. 4 minus 4/3 x minus 4/3 y, but my y is 6 minus 4x. Yeah, this is just algebra now, as usual. That's 4 minus 4/3 x minus 8 plus 16/3 x. That's a -4. I'm moving it over here. It's a +4. That's a 12/3 x, which is a 4. That's a 4. That's a 4. Divide by 4. I think x is 1. Whew. If x is 1, plug it in here. Guess what y is? 2. I love how it ends. This is a struggle. These problems are a struggle. They take a lot of work, a lot of little work, but at the end it all falls into place rather quickly. X is a 1, plug it in there, you find out y is 2, that's your critical number. And you don't have, that's your critical ordered pair, that's your critical number. Then I bet you that's the one that makes your volume be a maximum. What was the question? Find the volume. Okay, so they want the volume. Well, you got x and y. Maybe we need z. Here's z. Z is 4 minus 4/3. Remember, x is 1. And y is 2, so that'll make 2 times 2/3. That'll be a 4/3. Okay, so that's a 12/3 minus 8. So this will be 4/3. Z is 4/3. So your x is 1, your y is 2, your z is 4/3. That's awesome. If they wanted the dimensions of the box, we got the dimensions of the box. If they wanted the volume is x times y times z, right? X times y times z. The volume of this box that does this, is 8/3. That's the largest box that has a corner right there and sits in here underneath this plane. There's a plane slicing through here. And this box fits in that corner. It's got that volume. Jeez, that's a good question. I like that question. I don't know, I like all these questions. Max and min. I don't know, I think they're good. Now I can keep grabbing fun problems unless you guys got any requests anywhere. Any concerns or requests anywhere?
Is there any good ones to do with the second partials test?
Well, that's right. That's a good point. I haven't done that today anyway. Right. Well, so number 1 on your take-home quiz is a good one. I kind of would, I don't want to do that one for you. Let me see if I can find another one. On this practice piece of paper, is there a good one? Not really. No, there's not. All right, let me try to find one out of the book. So that's in 13.8, where we find all the critical numbers, and then we got to go find out, are they a max, are they a min, are they a saddle point? I'll tell you what, this number, let me see here. What did I do the other day? I did something. I did 10 or 11 or 12. I also did 18 the other day. 18 was kind of fun.
Is there going to be any questions where you just give us a graph and you want to ask what's the saddle point?
No. No, it'll be more like this one here. I found one here. Let's do this. Let's do this. So in 13.8, number 22 maybe. We'll see. It could get rough. We'll see how it looks. But give me this thing. It is 13.8. I found this 22. Y cubed minus 3yx squared. Y cubed minus 3yx squared minus 3y squared minus 3x squared plus 1 minus 3y squared minus 3x squared plus 1. Yeah, this is a good one. This is similar to maybe what I put on your take-home quiz and what you might see on a test. So what's the deal? Find all the critical points and classify them as mins, maxes, or saddle points. Right, that's your job. So, how do we look for critical points? We need the first partials, and we need to set them equal to 0 and solve this simultaneous set of equations. So here we go. We need these first partials. Okay, partial derivative with respect to x. Negative 6yx minus 6x. That's it. The partial derivative with respect to x. All right, cool. That was easy. All right, the partial derivative with respect to y. Partial derivative with respect to y. 3y squared minus 3x squared minus 6y. Yeah, with respect to y, that's it. All right, again, this is the part, I think, where y'all need the most help. Setting these equal to 0, I mean, I know this is the algebra actually here, but setting these two equations equal to 0 and solving this simultaneous set of rather nasty equations. So watch how I do this. Watch how this is going to play out here. Again, factoring sort of helps a lot when you set things equal to 0. So over here, I'm going to factor out a negative 6x, I guess. That leaves me with, that leaves me with y plus 1 equal to 0. So now when I set this equal to 0, watch, I'm going to get an answer called x equals 0. You know, when I set this equal to 0, I get an answer, y equals negative 1. Now here's the problem that students might do something wrong here. Listen, they don't go together. They don't go together. That's not an ordered pair. That's just when this derivative equals 0, there's an x value that makes it 0, and there's a y value that makes it 0. But I need to also find out when this one equals 0. So here's what, so to find the partners for x equals 0, it ain't him. To find the y values for x equals 0, what you do with this x equals 0 is you go plug it in here. And find the y values that go with x equals 0. And you watch what, you plug it in here, and now you're solving this simultaneous set of equations. 3y squared minus 6y equals 0. You factor out 3y, y minus 2 equals 0. This is algebra again, factoring. That y equals 0 and that y equals 2. They both go with this x. That's pretty cool. We're finding critical points here. And we just found when x is 0, y is 0. We also found when x is 0, y is 2. We found those two critical points. Guess what? There's more critical points. Remember, this equaled 0 when y was negative 1. Let's take that y equals negative 1 and go plug it in here. That's going to give me, when I plug y equals negative 1 in there, that gives me a 3 minus 3x squared. Okay, I'm plugging in a negative 1? Yeah, I'm plugging in a negative 1, so that's a positive 6. So I got this equation. 9 minus 3x squared equals 0. Let's solve it. Move the 3x squared over. Equals 9 divided by 3. X squared is 3. X is plus or minus the square root of 3. Those two x values go with this y value. So that leads to two more critical numbers. Here they are. Two more critical numbers. We found them all. When x is the positive square root of 3, and when x is the negative square root of 3, the y value is negative 1. Wow, that's pretty cool, man. That was a good problem. That is similar to the way yours works on your take-home quiz. You should kind of check that out. I mean, of course you're going to check it out. You're going to do it. But that's awesome. So now, guess what? These are my critical points. Hey, they might be mins, they might be maxes, they might be saddle points. And the way to test them is with this second partials test, which you don't have to memorize. I'll give it to you, but you might be worth practicing doing it. Let's see, the second partials test, well, first of all, to do the second partials test, what you do is you calculate this number b for each of these damn critical points. You do it for fxx. I mean, here's this number b. The number, and again, you don't memorize this, it's given to you, but d is fxx evaluated at the critical point times fyy evaluated at the critical point minus fxy evaluated at the critical point squared. So we calculate this number b. So anyway, I need all my damn second partial derivatives. I need all my second partial derivatives. I need fxx. I need fxx. Where is fxx? Where is fx? Well, here's fx. So how do I take this derivative with respect to x? Take this derivative with respect to x. Negative 6y minus 6. That's fxx. I also need fyy. fyy. Okay, here's fy. Take this derivative with respect to y. 6y minus 6. 6y minus 6. It's a little different, I guess. Okay. All right, I need fxy. fxy. Okay, that means go to fx and take that derivative with respect to y. Taking that derivative with respect to y. Negative 6x. Right. Okay. All right. Now what do I do now? Okay, so like I said, I calculate this d for each of these critical numbers. To calculate this d, I needed these three dudes here. Now let's sort of try that. Here I go. I'm going to do it for the point 0, 0. So for the point 0, 0, the d is. What are you doing? You're plugging the 0, 0 into the fxx. When you plug a 0 in there for y, you get a negative 6. You also plug the 0, 0 in for FYY right there, and you get a negative 6. Minus, you also plug the 0, 0 in right there. That means that x is 0, and you get a 0 there, and it is squared. Well, then, this d is a positive 36. This d is a positive 36. And I didn't write down that second partials today. I wrote it down the other day. But here's what it says. When the d is positive, but the fxx was negative, which it was, that was the fxx right there. So the d is positive, the fxx was negative. That leads you to a max. I think that's a max. So I'm done. This is a max.
That's something we have to memorize, right?
No, you don't have to memorize that. No. You get that. You get that, and you get the conclusions too. Right. Right. I'm giving you the whole second partials. Right. I'll give you all that. But I guess I got it memorized. Did I read it right? Did I say it right?
Yeah.
When the d is positive and the fxx is negative, that's a max. Okay. Again, you don't have to memorize it, but you can read it. Okay, cool. All right, well, now what do? You do this again for each critical number, right? So now I'm going to do this again for the point 0, 2. For 0, 2, we got to calculate the d. All right, that means plug your 0, 2 into your fxx. Now this time, the y value is a 2. So that's negative 12 minus 6. That's a negative 18. I've also plugged that point into the fyy, but now that's y is 2, so that's 12. That's a 6. And then I'm plugging in my x is a 0, so I'm plugging in a 0 there. That's 0. So that's 0 squared. Anyway, this is negative 108. But it's negative. And when d is negative, it's a saddle point. When d is negative, it's a saddle point. And you get that information, but that's what it says. Cool, we're done. Saddle point. I mean, we're done again. We got 2 more to check. We got to check the square root of 3, comma 1. Let's check him out. No, I'm sorry, it's comma negative 1. Square root of 3, comma negative 1 for y. And I'm going to calculate the d again. Here we go. Plugging a negative 1 in for the y, it's positive 6 minus 6, that's 0. Plugging a negative 1 in for this y, that's negative 6 minus 6, that's negative 12. Plugging a square root of 3 in for this x is negative 6 square roots of 3. It's negative 6 square roots of 3, but it's going to be squared, and then it's going to be subtracted from this, which is a 0. Now hold on. This is a 0 minus this. This is going to be some positive number. So 0 minus some positive number.
108.
Well, okay, but it's negative. And if it's negative, when the d is negative, it's a saddle point. Is that okay with you guys? This was a 0. You're subtracting some number squared. I don't care what it is. You're subtracting some positive number. It's going to be negative. If d is negative, it's a saddle point. Right. That's interesting. I bet the next one is the same thing, maybe. Let's see. The next one is the negative square root of 3, comma negative 1. That's the last one I got to test. I plug in that negative 1 again. I get that positive 6 minus, yeah, I get a 0 there again. I plug in that negative, I get that negative 12 again, but that doesn't matter really. That's going to be a 0, and you're going to be subtracting, I don't even care what, squared. I mean, I do kind of care. It's 6 square roots of 3. But it's some number squared. It's positive, and when you subtract it, it's negative when you subtract it from 0. So this is negative again. When d is negative, it's a saddle point. So that was, I mean, I don't know, man. That was kind of tough. It was kind of long. But it's a good problem. In a way, some of the algebra wasn't that tough. It was these factoring moves, or when you set these things equal to 0, you got to know kind of what you're doing here. This is a good example. I feel like that's kind of the hard part. Getting these critical numbers and getting the ordered pairs with the right ordered pairs. Which x's go with which y's, you know. And then once you got those, I don't think this is that hard. And especially if I give you the formula, you don't have to memorize it, but you got to check it. Yeah, that was good. That was worth going over. A good 13-8 problem. That was a good one. Anything else we should talk about? You know, those domains are kind of tough. Look at this. This is, you know, on your in-class quiz the other day, you had a tough time with the domain sometimes, some of you. Here's on my practice piece of paper, I got a domain question here on my practice. It says, can we sketch the domain of this? Dude, this is a good one. This is a real good one. You know, so sketching the domain is, it's about, it turns into, it's about messing around, messing around with these inequalities. But you got to start off with the right statement. What do you want to say right off the bat here?
The denominator can't be 0.
Good. So I think you want to say that the x squared minus the y squared, you know, actually he's in the denominator, but he's also in a square root. So he can't be negative and he can't be 0, so he has to be greater than 0. Right. The x squared minus y squared have to be greater than 0. And this is the part students aren't good at. They're not too good at dealing with these funny inequalities. I mean, these quadratic and cubic, these interesting inequalities. So I'm going to show you something. I'm going to show you that what you kind of can do is ignore the inequality for a minute. I mean, this is important, but now I'm going to ignore it. I'm going to pretend there's an equal sign, which is maybe kind of bad, but then I'm going to move the y squared over to the other side. I'm going to have x squared equals y squared. I'm going to take the square root, and I'm going to have y equals plus and minus x. And does that make sense to you? Move the y squared over, take the square root, and you get this. Because I guess you kind of want to solve for y so you can figure out what the hell to graph. And this is what I want to graph. I want to graph y equals x, and I want to graph y equals negative x. Now, in my original inequality, was it allowed to equal or was it allowed to not equal? In my original inequality, was it allowed to be equal? No. Okay, so when I draw these, they're not supposed to be equal. So I'm not going to draw solid lines. I'm going to draw dashed lines. But what are they? Y equals x is this. And y equals negative x is this. So what I've sort of found here is sort of the borders, you know, of my domain. Now I need to figure out which part to shade. Do you know how to figure out which part to shade? I would say that pick a test point. You pick a test point, and you go back to the original inequality you had set up. See, so I guess I ignored the inequality. Listen, here's my point. If you would have kept this inequality symbol here, you got this, you got this. I mean, when you start taking square roots and stuff, you can't trust the damn inequality anyway. That's why I just ignored it there for a few steps. I tried to solve for y. You can't trust the inequality when you square root and do a quadratic like this. So the less than or greater than symbol had no meaning for me here. So that's why I just sort of ignored it. And it got me the graph, or it got me the borders. But now I'm not going to ignore it. I got to figure out what to shade. Watch. Pick a test point out here, like 3, 0. If you plug that in, 3 for x, 0 for y, is it true or false? 3 for x, 0. You would get 9 is greater than 0, is what you would get. Is that true? Well, then shade that region, and that means that region. I mean, we only picked one test point out there, but that means the whole, and it came out true, so that region needs to be shaded. I bet you this one too, right, you guys? -3, 0, I bet you that works. because if you plug in a -3, that's 9, and that's greater than 0. What's funny is any test point would work if it's in this region. Any test point would work. But it's true. I'm shading this whole region. I don't really need to go any further, but just for fun, this would prove to you that this is not here. This is 0, 4. I'm going to try 0, 4. If I plug it in, that's a 0, that's a 4. You get -16. Is that greater than 0? No. Please don't shade that. Please don't shade that. You're finished. This is a picture of the domain of this function. I don't know what the hell this function looks like, but it lives over these regions. Yeah, that was a good one. Let's just review. You're on your in-class quiz. What was the function you had? On your in-class quiz for domain, you had, where is it? Oh, 2x minus y over y minus 2. 2x minus y over y minus 2. Look, see, I think sort of the hard part is sketching the domain. Actually describing the domain isn't hard. I think you guys would look at this and know this. 2x minus y has to be greater than or equal to 0 because it's inside a square root and it needs to be greater than or equal to 0. So you know that, so you state that. All right, here's the other thing you can state. That you don't want your denominator to be a 0, so you're going to say that y cannot be a 2. So in a way, this is you stating the domain. But what does a picture of all this look like? Well, in order to draw a picture, I would solve for y here. Now watch me, I'm going to move the y over. So 2x is greater than or equal to y, or you could write that backwards and say y is less than or equal to 2x. But see, now I know what to draw. I should draw the line y equals 2x and then shade one side or the other. Y equals 2x is a pretty easy line. It goes through the origin. It goes up 2 and over 1. Up 2 and over 1. And it's this line. Is it okay for me to make it a solid line? See, again, this is the border, but this time my border is solid because it's allowed to equal. So my border is solid, but I still need to shade one side or the other. Which side should I shade? I don't know, man. I don't know how, I don't understand, I can't read these inequalities too well. Y is less than 2x. It's probably this side. But I'll pick a test point. I'll pick a test point right here called 1, 0. So that means I'm plugging in a 1 for x and a 0 for y, and is that true? Yes. And if it's true, you shade that side. Awesome. Awesome, awesome, awesome. Wait a minute. Oh, there was one thing I forgot. I didn't forget it, but I sort of just did now. There is another. So there's your picture of domain, except for this little fact. Y is not allowed to equal 2. And by the way, that's a horizontal line. And so y cannot equal 2. You know what? It's kind of insignificant over here. We know it's not going to equal anything over here. Anything over here. But over here in my domain, there is a gap of stuff that is not in this domain. This dashed line where y equals 2 is technically not in the domain. So it's like shaded all the way up to that line, shaded all below that line, and so on. But I'm trying to exclude this line. Cool. That's the answer. That's good stuff. That's good stuff. What else? Any other ideas? Or requests? I can help you with anything. We got a little more time. We could quit early, or we could do more problems.
On the quiz, the practice quiz we did last Monday.
Yeah.
I forgot how to do the division rule, the quotient rule.
Oh.
I'm not gonna make you do that. I just need to do that.
Yeah. Well, right. And I've done one sometime in the last 2 weeks or so. I did a quotient rule because, and I might have done one or a couple of them because and then I said, I like quotient rules. So I like them. I can help you with that one. You mean on the quiz?
Yeah.
Yeah. What was it? It was x squared y, is that what it was?
X squared y over x squared plus y squared.
Right. So it's kind of a pain, but the quotient rule is, if I'm doing the derivative with respect to x, a partial derivative with respect to x, the quotient rule would be, you know, the derivative of the top. The derivative of the top with respect to x, 2xy. Okay, then times the bottom, minus, then you write down the top, times you take the derivative of the bottom. So I mean, that's the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom. And what's the derivative of the bottom with respect to x? 2x. All over the bottom, the denominator squared. So there you go. That's a quotient rule. I mean, in a way, it's not the worst thing in the world. You know, you just calmly do it. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. And then cleaning it up, just this guy, they do clean up a little bit. If you distribute this and collect like terms, it cleans up a little bit. Let's see. If I distribute this, it's a 2x cubed y plus a 2xy cubed. That's what happens when you distribute it. Minus, this is a 2x cubed y. Yeah. So that's completely gone, and so my final answer, I'm left with this term, this 2xy cubed over this. And that's just the fx. What's the fy? Similar, but different, but similar, but different. Let's try it. Let's see, the derivative of the numerator with respect to y. I think it's x squared. Times the denominator, minus, write down the numerator, and take the derivative of the denominator with respect to y, all over the denominator squared. So there you go. This one doesn't simplify as much here. Let's see, what this is x to the 4th. This is an x squared times a y squared. When you distribute this, and this is 2, negative 2, x squared y squared. So it is x to the 4th minus, right, one of these minus 2 of these is minus 1 of these, all over the denominator squared here. Yeah, that's good enough. That's cleaned up, that's good. That's your fx and fy. By the way, what I wanted in this problem was the gradient. In general. So I did want you to sort of write this gradient in general, which is basically, it's those two things put here in this vector format here. I mean, this is what the gradient is, fx comma fy vector here. Cool. And then I also wanted it all evaluated at a certain point, and anyway, so now you can do that. At the point, which was negative 2, 1, 4/5. At the point, negative 2, 1, 4/5. You know, I give you these points, but it turns out when you're plugging these numbers in, you don't need the z value. You need the x and the y. You plug it all in. Anybody? What was that answer? I think it was.
Negative 0.16.
Yeah. Or 4/25. What was the other one?
0.48.
Which was 12/25, I think. Yeah. That's what they were. But decimals, you gave me the decimals, the version, which is those numbers, I think, right? When you plug in the -2 and the 1. Yeah. So again, that's the gradient at any x, y, and here it is. This is the gradient at the point -2, 1 when we. So when you're standing at that point, when you're on this surface and you're standing at that point and you look in that direction, that's the direction of steepest slope. That's what the gradient does. It points you in the direction of the steepest slope. Cool.
And the magnitude of that is the actual slope, right?
Good. And the magnitude of that is the actual slope, some number, 6, or 5.3, or some little number, I guess. Yeah, that's the actual slope. It's not much in this one. I mean, these are little numbers. The magnitude's going to be small.
Yeah, 0.505.
Yeah. No. That's a small maximum slope. All right, that was fun. It's all fun. It's all fun. Anything else? Well, I might quit. I might quit today. I'll hit pause.